We start off our second half of chapter 8 discussion with doing few questions that's in our 18th homework assignment. The reason for that is Lewis-Dot structures and Vesper theory are the two most important topics that we have in chapter 8. These two concepts alone will make up almost half of the questions we will see in the third sections of our final exam. So that's just how important these two topics is, along with some other topics we'll discuss in this section later on, that will definitely make up more than half of the questions we'll see in the third section of our final. Therefore, chapter 18 is very important for us to understand. Our dilemma is we don't have much of time to understand it because the college has used 1 week for us to prepare the lecture and try to put the lecture online. But I just want to emphasize, go through the homework 18, and the first half of homework 19 is essential for us to keep up the decent grade in the third section of our final exam, because we just cannot afford to lose so many points in the third section, and they will hurt us as a whole as the grade of the final exam. So therefore, I just hope that you have the homework 18 nearby to you. And we're going to start off our third question in that homework 18, which is, so what is the molecular shape of SF4? In order for us to predict the molecular shape, there's a certain procedures that we have to go through. And we mentioned that at the end of our last discussion on chapter 8, and we know that first we have to write a valid Lewis structure. There are a few steps in writing Lewis structure. First step, we try to calculate just how many valence electrons we have for the molecules like CSF4, sulfur tetrafluoride. As we check out the periodical chart, we find out that sulfur is an element in group 6A, fluorine is an element in group 7A. That means sulfur will have 6 valence electrons, or 6 dots, while fluorine will have 7, combined with the subscripts of each atom in this formula. So we start our calculation and we find out there are going to be 34 valence electrons that we're going to assign back to this formula. Second step in drawing a valid Lewis structure is choose which atom that we should put into the center, sulfur or fluorine. Apparently, there are two ways for us to determine why sulfur has to be in the central atom. First, sulfur is a less electronegative, so it has to be the central atom. Second, if we recall what we have discussed about fluorine being the terminal atom or surrounding atom only, the reason for that is the fluorine requires only 1 bond. So fluorine cannot be the central atom because central atom must have at least 2 bonds. So based on these two reasons, we can easily determine it is the sulfur that we have to put in the center. SF4 means 4 fluorine atoms, so that is why we can set up sulfur in the center surrounded by the 4 fluorine atoms. Now, our next step is to give electrons back. Remember, we have total 34 valence electrons to distribute. As a first step in this part, we're going to form 1 single bond for each pair of atoms. That means we only give 2 bonding electrons for each pair of atoms. And of course, in chemistry, we prefer to use dash to represent those bonding electrons. So single bond between each pair of bonding atoms. As we count, we used up 8 valence electrons by connecting sulfur with the 4 fluorine atoms. We have 34 valence electrons total, so we have way more electrons to distribute. So into the second step of this portion, for the rest of the electrons, we give enough electrons to surrounding atoms so that they can attain the octet. Duet for hydrogen. Because we have fluorine atoms, that means fluorine requires an octet for each of these 4 atoms. We have to give 6 more electrons to each fluorine, as you see in the animation. With the 2 bonding electrons and these 6 more electrons we just assigned, fluorine will have an octet. This is the most important part for writing a Lewis structure, because most of the time, I'd like to say 98% of the time, there are enough valence electrons for us to give terminal atoms to make them octet. So it's pretty safe for us just to give electron to the surrounding atoms to make sure that they have the octet. Then we only have to take care of the central atom, this only atom that we have to take care of. Now let's count just how many electrons that we have used so far. Remember, 6 electrons for each terminal atom fluorine. Total number of fluorine is 4, so we have 24 electrons being used. With the 34 electrons, 24 of these going to the 4 fluorine atoms, and 8 electrons using for bonding. Subtraction leaves us, there are 2 electrons left. That 2 electrons has to go to the central atom. So here I just put these 2 electrons in a very bold, obvious way for you guys to realize sulfur does have a lone pair of electrons of its own. Why? Because there are 2 electrons that has to go to the sulfur as a lone pair. As the last step, in order to take care of the octet of a central atom, we understand that if there are less 8 electrons on the central atom, we have to move along pair of electrons from the terminal atom to the bonding position. That means we're going to introduce double bond, sometimes even triple bond if we have to. We had that in our example for writing Lewis star structures to the molecules like a carbon monoxide or cyanide. And as you may realize that sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sulfur has 10 valence electrons. That is not an octet. Octet requires only 8 electrons. Is that going to be the problem? This is something that we're going to discuss later on in this lecture. But here, I just want you guys to settle for this statement. If element of the central atom is in the 3rd period or lower, sulfur is in the 3rd period. When I say lower, that means the period 4, 5, 6, or 7 in the periodic table. It is possible for the central atom to have an expanded octet. Why? This is something that we're going to explain later on. So here, let's just settle for this statement. So say it's okay for sulfur to have 10 valence electrons, as we call it, expanded octet. All right, we just got ourselves a valid Lewis structure, although we have some concern about 10 valence electrons on sulfur, but that is valid. So if we move on to the next step, we're going to focus on the electron groups around the central atom. So that is why, as you can see, I take off the fluorines along those lone pair electrons on fluorine, because these are the things that we don't have to concern. We have to focus on the sulfur because this is a single atom. It has a limited space with so many electron groups around it. There's going to be a way to arrange those electron groups in order to minimize the repulsion among all the electron groups that sulfur has. Just how many electron groups that we have on sulfur? 2 different types of bonding and lone pair electrons that we need to count. First, let's count the number of bonding pairs. When we talk about bonding pairs, it doesn't matter whether that is going to be single bond or double bond or triple bond. As we see here, even though if we had a triple bond, it still occupies one side of this sulfur chemical symbol. That means they are in the same, they share the same space. So we treat such bond as one electron group. That is critical for us to count number of bonding pairs correctly when we try to answer the shape of the molecules using VSEPR model. How many bonding pairs do we have here? And easy way for us to do is circle those bonds. If we do 4 circles, we understand that there's going to be 4 bonding pairs. We circle double bond, triple bond, same way as we circle single bond. Is there any lone pair? Yes, because sulfur does have a lone pair. Adding up, the total number of electron groups around the central atom will be 5. There are 5 electron groups that we see on the sulfur, which is a central atom. What kind of electron group arrangement that we have? 5 electron groups result trigonal bipyramidal, and we have ideal, or in our last lecture I called it typical bond angle, 90, 120, and 180 degrees. This step is also equally important because we need to stick with the electron group arrangement that we choose to derive the molecular shape. Depends on just how many lone pair electrons we see on the central atom. Since it's a new slide, I'd like to remind you that we have 5 electron groups on the central atom. The arrangement or the geometry for such 5 electron groups will be TBP, short for trigonal bipyramidal. Without any lone pairs we see, the molecular shape is going to be the same as the arrangement. How do we know there will be no lone pair here? Because we just find there are 5 terminal atoms. 5 terminal atoms with the 5 electron groups. That means each electron group is a bonding pair. So the number of a bonding pair is a 5, number of a lone pair is a 0. Only with a 0 lone pair can we have the same molecular shape as the arrangement of this electron group on the central atom. As a bond angle, we understand that it's going to be 90, 120, and 180. But here, do we have a less than or equal? Without any lone pair, it's equal, always. Those are the ideal bond angles, determined by this very specific, highly symmetrical geometry. All right, now what happens if we do have a lone pair like this? So this is our lone pair, still sticking out, occupying space because it's a pair of electrons. However, there's no bonding atom on the other end. If we pretend we cannot see it, as a matter of fact, we cannot detect it, so we cover it up, say we cannot see it, the molecular shape will be seesaw. And number of bonding pairs, that'll be 4, lone pair, that'll be 1. And that lone pair occupied the equatorial position as we already discussed before. For bond angles, with a much less symmetric geometry like seesaw, the bond angle is gonna be always less than ideal angles, bond angles. Always. Unless we find out there are enough of lone pairs that make the geometry back to highly symmetrical again, which we will see that later on as we're going through pretty much all the molecular shapes that we can derive from this particular electron group arrangement, trigonal bipyramidal. So from what we have discussed, we realize that the one on the left here actually is the electron group arrangement. Regardless of whether there's going to be bonding atoms or not, there are always going to be 5 electron groups. These 5 electron groups will be, as always, trigonal bipyramidal. And on the right, we have molecular shapes. Molecular shape is determined not only by the electron group, also determined by the lone pair. If you do not like a number of lone pair, you can say it's determined by the bonding atoms. Because we start to see fewer bonding atoms. From 5 now to 4, and we can have 3. Because we just realized there are 2 lone pairs in equatorial position. As we cannot see them, the rest is T-shape. 2 lone pairs occupying the equatorial position, that gives 3 bonding pairs and 2 lone pairs. And of course, the bond angle, T-shape, is not a so-called highly symmetrical shape or geometry, so it's going to be less than. 120 degrees is gone because there's no trigonal plane anymore. All right, since it's a new slide, okay, so I just put everything together before we move on to the last molecular shape. So we understand if we have a 0 lone pair or 5 terminal atoms, and the shape is going to be trigonal pyramidal, same as the electron group arrangement that we choose. Molecular shapes are going to be seesaw if we see only 4 bonding atoms, right? 1, 2, 3, 4, 4 bonding atoms, so 4 bonding pairs with 1 lone pair. The molecular shape can be even derived downscale to T-shape if there are 2 lone pair of electrons. 3 bonding pairs now, well, 3 terminal atoms now. And of course, we can have 2 bonding pairs where we can have 3 lone pair of electrons. All these lone pair electrons, as we can see, occupying the equatorial position. Now we have linear. Linear is one of the most symmetrical shape we can find. Speaking of bond angle, there's only 180 degrees, and it's always equal because it's a linear. As you may realize, we just have gone through all the possible molecular shape we have with 5 electron groups, starting with the trigonal bipyramidal. Because it is a trigonal bipyramidal that has been set, and then we can derive the related molecular shape depending on just how many lone pair of electrons, or if you do not like it, you can say just depend on how many bonding atoms that we can see from such geometry. Let's go back, take a look at the sulfur tetrafluoride. What is the molecular shape for such molecule? As we recall, there are 5 electron groups on the central atom, which is sulfur, 4 bonding, 1 lone pair. That makes this one. Seesaw. All right. So from this problem we used as an example, one of the most important things I like to point out is we determine the electron group arrangement first. Just like we have a mammals. Pretty much all the mammals has a head and 4 limbs. How can we tell? Right? So we need to differentiate the mammals out from the other species of the animals. Then we can say, okay, so this one is a dog, the canine. This one is cats, feline. So those canines, so those mammals actually is what we called molecule. So I'm sorry, the electron group arrangement. We have to determine the species is a mammal first before we can differentiate whether they are cats or dogs. Cats or dogs are pretty much like the molecular shape in our case. So I just want you guys to understand which one comes first. It is electron group arrangement comes first, like a mammal. And then we go to even further to differentiate what class those animals are. Okay. I'd like to use question 10 as our second example. The reason is I just want you guys to realize this is an ion. Okay. So we're going to count the number of valence electrons slightly different from the question 3. Again, it's always writing a valid loose structure coming up first. Remember the procedures? I hope that you already get used to this way of doing things. Total number of valence electrons. We got nitrogen, group 5A, 5 dots, oxygen 6A, 6 dots. According to the formula, alright, so we got 1 times 5, 1 nitrogen, 5 dots, 2 oxygen, 6 dots. But here, y plus 1, because there's 1 negative charge there. So that is the reason why we need add 1 electron for each negative charge of the anion. Okay. So total number of valence electrons is 18. Second step, we set up atoms. Which atom should go to central position? And we understand it's nitrogen. Why nitrogen? Because nitrogen, oxygen, they are in the same period where oxygen sits on the right-hand side. Remember, electron activity increases as we go in the period from left to right. Oxygen has a higher electron activity than nitrogen, so nitrogen sits in the middle. So this is how we arrange nitrogen with the 2 oxygen atoms. As As we distribute electrons, we put a single bond between two pair of bonding atoms. Nitrogen with oxygen on the left, nitrogen with oxygen on the right. We used up 4 electrons. As we try to make octet for these 2 oxygen atoms, we used up total 12 electrons. And the overall number of valence electrons we're going to distribute back is 18. So 18 minus 4 minus 12. So here is the 4 minus 12. We have 2 electrons left. The 2 electrons goes nowhere by the central atom. Is nitrogen an octet yet? Apparently not. That means one lone pair of oxygen has to go to the bonding position. Say the bottom pair of oxygen, bottom pair of lone pair of electrons from oxygen on the right going to the bonding position. This way, we have a double bond set up between nitrogen and the oxygen on the right. Double bond 4 electrons, single bond 2 electrons with a lone pair electron on its own. Nitrogen now attain the octet. Nitrogen is another and third period element, so this statement doesn't work for nitrogen. And we're going to move on to our next phase, which is counting electron groups on nitrogen. So here I just lay out those electron groups, the bonding situation in lone pair that's on the nitrogen, the central atom. Number of bonding pairs, how many? I hope you guys determine there are only 2. Remember, double bond, triple bond, just like a single bond, they all occupy one side, only one side of a chemical symbol of nitrogen or central atom. Since it's only occupy one side, we count them as one electron group. All right, is there any lone pair? Yes, there's 1. So total number of electron groups on the central atom, 3, because 2 plus 1. We have a total of 5 fundamental electron group arrangements to choose from. We got 3, so we picked 3 electron groups, which is a trigonal planar to begin with. The ideal bond angle, 120 degrees. All right, remember, 3 electron groups, our template is trigonal planar. Just like this particular group, like they're beetles, right? So 6 legs. All right, so what kind of molecular shape that can come with this 3 electron group we lay out as trigonal planar? Of course, molecular shape can be trigonal planar as long as there's no lone pair of electrons. All 3 electron groups are bonding pairs. Why? Because we got 1, 2, 3 terminal atoms. 3 terminal atoms are 3 electron groups. They are all bonding pairs. Bond angle is going to be equal 120 degrees. Because this is one of the most symmetric geometry that we can have. Well, just what other molecular shape can we have? It depends on just how many lone pair electrons we can have. That's on the central atom. How about if we have 1 lone pair of electron on the central atom? And after we take away the lone pair, so this is what we see for an entire molecule, as we call it band. Now we understand the band has two bonding pair with one lone pair. Bond angle has to be less than 120 degrees because the presence of lone pair will make the bonding angle less than the ideal bonding angle, unless lone pair of electrons, if there are enough, to form a highly symmetrical geometry again, like a linear, like square planar. These are pretty much the two exceptions for the bonding angle going back to its ideal bonding angles. Can we have two lone pairs for three electron groups? It's very much unlikely. So that is all for molecular shapes that we can derive from trigonal planar as electron group arrangement for three electron groups. So one way for us to understand this electron group arrangement is electron group arrangement is determined by the bonding and the lone pairs of electrons combined. As for molecular shape, it can be only determined by the bonding pair or the surrounding atoms. Because when we talk about molecular shape, we describe the spatial arrangement of those bonding atoms. In other words, bonding pairs. Okay? Again, determine electron group arrangement first, then we talk about molecular shape. Going back to our question, nitrite ion NO2-, we now see there are two bonding and one lone pair that would be bent. And I'd like to remind you the bond angle is in the neighborhood of 120 degrees. Because we can have two bent molecular shape coming from different electron group arrangement. All right. I just hope that these two examples we have just went through could give us some better, some understanding that we can deal with those questions better, especially the homework 18. I believe homework 18 has a due. Okay, so I just want you guys to know that we need to submit this homework 18 because this is going to be counted towards our overall grade. Okay, now let's pick up what we have left from Lewis' structure. And we're going to take another look of our second example problem, writing Lewis structure for carbon dioxide. And we understand, if you still recall, we have total 16 valence electrons, and we put carbon in the center, surrounded by two oxygen atoms. As we distribute electrons, single bond between each pair of carbon and oxygen. There are totally two pairs. And for the rest of the electrons, we give enough electrons for each oxygen to make sure they have the octets, and we are out of electrons. This way, carbon is going to ask one lone pair from each oxygen to go into the bonding position so that the carbon can have a double bond with each oxygen. In this way, we realize carbon has an octet by sharing 8 electrons. Oxygen can have an octet by having 4 lone pair electrons. 4 lone pair electrons. 2 pairs of lone pair electrons. And 4 bonding electrons. This is what we did for this example back in our first half of our lecture. But when we look at it, we find out that that may not be the only choice for carbon to gain 2 lone pair of electrons. Why? Because for each oxygen, as we see, each of them has 1, 2, 3 lone pairs. Let me put it this way. The oxygen atom all by itself can give up 2 lone pair of electrons. If that is possible, we are talking about a triple bond between the oxygen and the carbon instead of a double bond. Because once oxygen gives up 2 lone pair of electrons to the bonding position, there will be total 6 bonding electrons. That means a triple bond. If oxygen on the left can give up 2 pair of lone pair electrons, the oxygen on the right can do that too, because this is the same oxygen atom. All right. All of a sudden, we find out that there are 2 more choices. Which one is valid? In short, they all are valid. Because I cannot find any other error to point out that Lewis-Dot structure is wrong. Remember, when we write up Lewis-Dot structure, our automatic goal is octet for each atom. And in certain particular cases, we can tolerate the central atom having more than 8 valence electrons, as we call it expanded octet. But nevertheless, octet for all atoms, duet for hydrogen, of course. That is our automatic goal, to write the valid Lewis-Dot structure. And all 3 Lewis-Dot structure we derived here, or we just wrote here, they all valid. How come can we have this kind of situation? One simple compound, CO2, can have 3 valid Lewis structures. This situation is what we call the resonance form or resonance structures. They are pretty much the valid Lewis structures with a different arrangement of electrons. In short, different type of multiple bonds. So for example, we got a single bond and triple bond on the central atom, and 2 double bonds on the central atom. So we talk about a different arrangement of multiple bonds. That is what the resonance structures for. For actual molecule, that would be the combination of all resonance forms, even though we can see that some of the resonance may have a different weight than from the others. This here is a model of carbon dioxide. And if we look at the distance between the center of carbon to that of oxygen, so we said that is about the distance. And I use different color, okay, to show the distance between the center of carbon to the oxygen that's on the left. And it's turned out those 2 has the same length. Same length, that means that the carbon with the 2 double bonds will have more weight in these resonance forms. Because the single bond and triple bond, they might have some difference in the length or the distance between the centers of this bonding pair of the pair of bonding atoms. So that is going to be a very good example for us to realize the resonance form could have a different weight in the actual molecule. So how are we going to do this? We just put them all together, lay them all out, connect them with the double arrow. Say, okay, so this structure can be resonate from one end to another and bouncing back and forth. Let's try out with another example using the concept of resonance forms. SO2. Both sulfur and oxygen are in group 6, means there are going to be total 18 valence electrons. Sulfur is less electronegative because down the group, electronegativity decreases. Oxygen has more electronegativity. Oxygen goes on the surrounding positions. And as we distribute electrons, remember our first step is only single bond for each pair of bonding atoms. That's 4 electrons. Our next step, make sure terminal atoms like oxygen attains octet. 4 electrons plus 6, that's a 10, plus another 6, that's a 16 electrons. And the last 2 electrons will go to the sulfur. That's all for 18 electrons. And we just realized for sulfur here, it's 1, 2, 3, 4, 5, 6. It's not an octet yet. And the sulfur could have 2 choices to ask a pair of electrons from oxygen to join into the bonding position. Oxygen from the left, 1 lone pair goes in, and we can have a double bond between sulfur and oxygen from the left. The oxygen on the right can do the same, so we can have a double bond between sulfur and oxygen from the right. Speaking of a resonance, we got 2 valid loose structures as the resonance forms. I'd like to try out another example with the resonance because the resonance can bring us at least 3 questions in our final exam. For third section, of course, for example. Okay. And how many resonance structures that we can get? How are we going to write the resonance structures? Which one has more weight? Right? So there are 3 types of problems that is closely related to the resonance structure. The resonance structure is a simple enough concept, but that can give us more questions in our final. So this is something that we have to understand. Let's try one more problem as an example. This time we talk about a nitrate. All right, so as for nitrate, nitrogen, oxygen, just like a nitride we tried before, total number of valence electrons is going to be 24. Why do we have to add one more electron? Because there's 1 negative charge right here. Set up atoms, nitrogen is less electronegative, goes in the center, surrounded by 3 oxygen atoms. As we distribute electrons, single bond all around, as I used to call, for all pair of bonding atoms. Each oxygen will gain 6 more electrons so that every oxygen atom will have the octet. That's it for total 24 electrons. Again, nitrogen is a 1 pair electron short because nitrogen has 6 dots around. 1, 2, 3, 4, 5, 6. Since it has 6 dots, and it is quite possible for nitrogen to ask a lone pair electron from any one of the 3 oxygen atoms. That means we've got a total 3 possibilities to form a double bond between nitrogen and oxygen. Put them all together, we have 3 resonance forms for nitrate. That's it for the resonance forms. However, remember, as we said, once we have the resonance form, it is quite possible that we can have one resonance having more weight than the others. Is there any systematic way for us to pick out that particular resonance, as we call most acceptable resonance structure? Why? Because we use the most acceptable resonance structure to represent this particular molecule for most of the time. As for carbon dioxide, we would prefer to use carbon with a 2 double bond with oxygen atoms as the typical or the loose structure for most of the time. Well, as we already discussed, by checking out the shape of this molecule, we find out the same distance between the centers of carbon and oxygen from each side. We realize the one in the middle could have more weight than the others. But can we do that with math? Remember, for science, math is the ultimate way to prove things. If something is being proved by mathematics, there's no more argument of whether that is going to be wrong. And it has turned out that there is the math for us to pick the most acceptable resonance structure. It could be many other names, most favored, okay, and so on and so forth. The concept that can help us to pick up the resonance structure as the most favored is formal charge, Fc. It is the charge of an atom would have if the bonding electron were shared equally. From that statement, we can actually write up a mathematical equation for it. The formal charge, and we must have a reference. The reference will be atom itself, so that means the number of valence electrons in free atom. And there are only 2 possible ways for electrons around such atom. Could it be lone pair? Could it be bonding pair, right? So we subtract the number of lone pair of electrons, not a lone pair, electrons in the lone pair. That is important. And we subtract the half of the number of bonding electrons. Why the half? Remember, the bonding electrons were shared equally. So from this definition, we can write up the mathematical equation for the formal charge of an atom. There are too many words in this formula, and I intend to use a few words I hope that can also make more sense. Let's look at this one by one. Number of valence electrons in a free atom. How do we know the number of valence electrons in an atom? You got it, group number. All right. As for the number of electrons in a lone pair, okay, it's easy for us to just count, right? Speaking of a half of a number of bonding electrons, I just want you guys to think of the bond in this way. We understand if we have a 2 bonding electron, we call it a single bond. Single means one. Half of the two, remember? Two bonding electron. Half of the two is one. How do we call one? Single. All right. How many bonding electrons do we have in, say, a double bond? 4. 4 bonding electrons. Half of these, 2. 2 is what? Double. And of course, we can do the same with, we can argue the same for a triple bond. This way, what we can do is, instead of subtract the half number of bonding electrons, we can simply subtract the number of bonds. If that's single, minus 1, double, minus 2, triple, minus 3. And there's also a trick for the formal charge of an atom. When we add up the formal charge of all atoms together, it should be the charge of the species. Why can't I say molecule? Because we could have polyatomic ions as well. If we talk about a molecule, the overall charge or the sum of a formal charge from each atom must be 0. If you have a polyatomic ion, the sum of formal charge must be equal to the charge of that polyatomic ion itself. And this equation here could give us a much easier way to calculate the formal charge under certain circumstances, as we'll see later on in our example. All right. Which one of these 3 resonance structure for carbon dioxide should be picked as the most favored, or what do we call it? That's just the most favored resonance form. Remember, we have this equation. And what are we going to do here? And what we're going to do here is to calculate each atom using that formula. We're going to start off with oxygen right here. Single bonded oxygen. So the formal charge of the single bonded oxygen, the group number of oxygen is a 6. Number of electrons in lone pair, there are 3 lone pairs. That's going to be 6 electrons. Single bond, so there's 1 bond, minus 1, that's minus 1. That means the formal charge of this single bonded oxygen, minus 1 for its formal charge. Let's do carbon. Carbon, group number 4. Electrons in lone pair, none, so that's 0. How many bonds? 1, 2, 3, 4, so that's 4 bonds. 4 minus 4, 0. That would be the formal charge of carbon. What's the formal charge of oxygen, triple bonded? Let's do that. Oxygen again, group 6. 2 electrons in lone pair, so minus 2. And we have 3 bonds for this oxygen, so minus 3. We have plus 1. Plus 1 it is for the formal charge of the triple bonded oxygen. And I'd like to remind you, when we add all 3 numbers together, it's a 0. It has to be 0 because the sum of the formal charge of each atom is equal to the charge of the species. We just talk about the molecule, so the charge of a molecule is 0. We find out that the resonance structure on the other end is very much like the one that we have just calculated. Only the triple bond, that single bond has a different position. All right, so we just move over there. Single bond in oxygen, it's minus 1. And a carbon is 0. And triple bond in oxygen is plus 1. All right, now let's move to the resonance structure in the center. double bonded oxygen. When we do double bonded oxygen, group 6 for oxygen, and 1, 2, 3, 4, 4 electrons in lone pair, double bond, -2, that's a 0. Without any further calculation, it's easier for us to recognize carbon must be the 0 as well. Remember, when we add up those zeros together, and with that formal charge of carbon, it must be 0. So the formal charge of carbon must be 0. And it also be proved using mathematics. Now we have the formal charge of every atom calculated in all resonance form. Just how are we going to be able to choose the most acceptable resonance structure or most favored resonance structure? First, we're going to choose the one with the smallest overall absolute value of formal charge in such resonance. This, as you may realize, is what we call the absolute value. It doesn't matter the sign. If it's -1, we take as 1. If there's a +1, we take as 1 too. But in this way, we find out the overall absolute value of formal charge in our first one is 2, right? So 1 plus 0 plus 1, that's 2. Here is 2 as well. And we find out the one in the middle actually is a 0. So from this calculation, we realize that 0 charge is mostly preferred. In other words, the more 0, the better. If we turn out 0 for all atoms, that's got to be the one. There's going to be no more than +2 or -2 charge on a single atom. The rationale for this is we're talking about a covalent bond. How much more charge can we get, right? There's got to be the limit. Because if we build up too much of charge on one atom, we should think about ionic bonding instead. So we put a limit, +2 or -2 charge on single atom when we apply our calculation of formal charge to it. And another criteria that can help us to choose the most acceptable resonance structure is atom with the more electron activity should have negative charge. Makes sense. Fluorine will do anything to grab an electron from the other atom so that it can have an octet. If there has the charge, it's got to be fluorine, because fluorine will do anything to get that electron. And fluorine is the most electronegative element. So it must have a negative charge. If there's negative charge needed to be assigned to an atom. When we pick the most acceptable resonance structure, we need to avoid the like same charge on adjacent atom. For example, ++ in 2 neighboring bonding atom, or 2 negative charge in the bonding atom. The reason for that is if you have the same charge, they're going to repel each other. There will be no covalent bond in this way. With these 3 criteria, the most important one will be the more zeros, the better. The carbon with the double bond is preferred. It's preferred. That one should be the most acceptable resonance structure. For the sake of a final exam, I strongly recommend you guys to memorize those shortcuts of formal charge, particularly on oxygen. As we already calculated, I just want you guys to understand single bonded oxygen has formal charge always -1. Double bonded oxygen has a formal charge always 0. Triple bonded oxygen has a formal charge always +1. I want you guys to memorize the formal charge of oxygen in these 3 different bonding situations. That's going to save us a heck of a lot more time, and also that give us a much better confidence to convince us that we calculated right. All right, let's try the formal charge with this example. This compound BF3, boron trifluoride. Total number of valence electrons, we got 1 boron and 3 fluorine. Boron, if I remember correctly, is in the group 3A. So 3 times the 3 fluorine with 7 valence electron each, so total number of valence electron is 24. Boron is less electronegative, obviously, because fluorine is the most electronegative. Fluorine becomes the terminal atom, and by the way, fluorine cannot be the central atom; it has to be the terminal atom. As we set up electrons, distribute electrons, boron, so it requires 3 single bonds to have boron and fluorine all chemically combined, can be bonded. 6 more electrons on each fluorine here, and we suddenly realize we used up all the electrons, all 24 electrons. We realize the boron is not an octet yet, right? 1, 2, 3, 4, 5, 6. So that's 6 electrons. And yes, boron will ask one of the fluorine to give up 1 lone pair of electrons for bonding. And here, we just use the fluorine on the top to form a double bond with the boron, and we understand that's going to be 2 more. But that example is typical enough for us to make a point. What kind of point should I make here? Let's go with the formal charge. Remember, formal charge is group number minus the number of electrons in lone pair minus the number of bonds. Let's check out those fluorines. We got a double bonded fluorine and a single bonded fluorine. And for single bonded fluorine, group number is 7. 6 electrons in lone pair with a single bond. The formal charge of fluorine is 0. If that is 0, this single bond fluorine is 0. What about the double bonded fluorine? And it has turned out the formal charge is +1. 7, 4 electrons in lone pair, so 7 minus 4. 2 bonds minus 2, we got a +1. What do you think the charge of a boron? Remember, when we add up a formal charge all together from each atom, it must be 0, right? Because it's a molecule, charge neutral. If one of the fluorine is +1, boron must be -1. Suddenly, we realize something is not right. If there is a negative charge, negative formal charge needed to be assigned, it has to go to where? Fluorine, you're right. Not a boron. What's wrong with this? Well, one way for us to do is we look back for this structure. We understand the boron has not an octet yet, but let's just simply check out what the formal charge of this structure. Remember, the single bonded fluorine has a formal charge of 0. So we got 3 out of 4 bonding atoms with a 0 formal charge. Boron, 0 as well. Between these two, which one is the most favored one? Most preferred one? Right? Of course, remember, the more 0, the better. Boron trifluoride will stay in this particular loose structure as most preferred, in which boron does not have an octet, because this is the most favored according to our rules in picking the resonance structure. And that definitely is another exception. Speaking of the exceptions of the octet rule, we now realize we got two of those. First, expanded octet. That means central atom must be in the third period or lower. That means the third or fourth or fifth or seventh. And we can use this loose structure of sulfur hexafluoride as an example. After we finish all of this, we realize sulfur has 12 valence electrons. Remember the SF4 we did, sulfur has 10 valence electrons. Either way, we find out sulfur has way too many electrons for an octet. Any explanation for that? Why this element has to be the third period? Remember, third period means n equals to 3. If n equals to 3, 3 subshells. We go all the way back to chapter 6 now. N equals to 3 subshells, S, P, and D. 3D as a subshell is there. It's just like have no electrons here. So those empty orbitals in the 3D subshell can, as we think, should accept to have electrons to go into. In other words, for elements that has the capability to have a D subshell, expanding the octet becomes the reality. What happens if you have atoms in the second period? Is that octet and octet only? Yes, because for elements in the second period, n equals to 2. There's no D subshell for that. Remember, for D subshell to appear, n must be 3 and more. So now we realize carbon, nitrogen, oxygen, once they become a central atom, including boron if we have to, they cannot have expanded octet, period. All right, so now we realize that with the help of 3D subshells, central atom can have more than 8 valence electrons. Boron trifluoride is the one example in this exception for octet rule we listed as electron deficient compound, or we call the compounds as incomplete octet. For this particular group of compounds, we should be able to see the central atoms like beryllium, even worse, right? It's group 2. Boron, aluminum. The elements show up in group 2 and group 3. In this example, this is what we call the borane, and there are only 6 electrons. And we know for sure as chemists, this compound does exist. It's not stable though, but it does exist. That means boron is okay to have an incomplete octet. With the 6 electrons, of course. The third exception would be the odd electron molecules. Odd number of electrons is what we call radical. So we call radical compound. For example, nitrogen monoxide. When we calculate the total number of valence electrons, 6 plus 5, that's 11. No matter how hard we try it, there's always going to be a single dot. on one of the atoms. Such compound is called radical. And because of this, imagine if we have another NO on top with a single dot as they approach each other, and there's going to be bond. So we have two NO to form N2O2 as we call it dimer of this compound, DIMER. This compound can be formed very easily. And the same situation occurs in a nitrogen dioxide as well. Because one nitrogen, 5 dots, 12 dots from 2 oxygen atoms, so that makes total 17 valence electrons. Again, nitrogen is going to have a single dot. So nitrogen monoxide and nitrogen dioxide constitute the typical example for us to understand radical incomplete octet. These are the 3 exceptions to the octet rule, and we are okay with them because this is something formed beyond the control of those atoms. All right, so that marks the end of the materials that is covered in our final. Okay, so slide number 16 is the end, okay, of the material that is going to be covered in our final. And for the next few slides, I'd like to talk about the polarity of a bond and the polarity of the molecules, just for some who is going to take organic chemistry as well as Chem 2 class later on. Before we talk about all this, I'd like to summarize what we have talked about so far. Loose dot structure is fundamental for chapter 8. If we write the loose dot structure wrong, there's no way for us to get the Vesper theory correct, and later on there's no way for us to get the polarity of the molecule or bond, polarity of the molecule right. It is very important for us to write the correct or valid loose dot structures first. Speaking of loose dot structure, we understand that we need to assign a dot for each valence electrons that we have for the element. The first 4 dots must not be paired. They occupy each side of the chemical symbol to show they are not paired. And starting from the elements in groups 5A to all the way to 8A, we start to see the pairing of those dots. Elements in the same group, they must have the same number of valence electrons as we discussed in chapter 6. They must have the same number of dots, and they must have the same dot configuration as well. And the octet rule applies to the elements in the p block. For the hydrogen, the s block element, duet is sufficient. And as we write the loose dot structures, remember, we calculate the total number of valence electrons as a first step, and we're going to add electrons or subtract electrons for the charges. And we set up the central atom with the least electron activity. Of course, hydrogen can never be the central atom, just like fluorine, because they both only requires 1 bond and 1 bond only. As we distribute electrons, all right, so there's 3 ways of doing this, 3 steps of doing this. First, single bond all around for each pair of bonding atoms. We are going to have more electrons. So what we're going to do is to make the surrounding atoms octet. If we still have electrons, and then electron goes to the central atom. And central atom would be the only atom that we have to care about the octet. So the octet for the central atom, with the exceptions of boron, beryllium, aluminum, and so on and so forth. As we move up at the lone pair of electrons from terminal atoms, this is how we're going to form the multiple bond. And this is probably the cause for us to have the resonance. For ions, we break every valid loose structures that we call the resonance, if there's any, and put the charge on the upper right corner to show actually it is ions, or they are the resonance structures for this ion. And we can calculate the formal charge to find out which resonance structure is the most preferred or most appropriate structure. Now, as you can see, we got so many names for the structure that we want to pick. And as we try to use the Vesper theory to predict the shape of the molecule, and we start with a valid loose structure. It may not have to be perfect. All we need is just one, as we'll see that in one of the example there. And we're going to draw the structure, and we count the electron group on the individual such essential atom. And by counting lone pairs, bondings, remember, we determine electron group arrangement first. And we're going to derive molecular shape from such arrangement based on the number of lone pairs. And we can also predict the bond angle if that's symmetric. So we have an ideal bond angle. For not so symmetric, because of the presence of a lone pair, the bond angle must be less than the ideal bond angle. And of course, if we have a multiple essential atom, usually we got yourself overlapping polyhedrons like ethane. We got two distorted tetrahedral overlapping with each other. And that is the start of organic chemistry. So I'm going to leave the rest such compounds or group of such compound for organic chemistry. All right, now let's take a look at this example. So we have ClO2, we call the chloride. As we are getting closer to the final, and I just want you guys to realize we need to prepare our materials for the final. We need to know the nomenclature of the final exams because it has been so long for us to practice. Okay. Remember, our first step is write a loose structure. So total number of valence electrons, because there's negative charge there. And we add one more electron to it, so total number of valence electrons is 20. And this is the loose structure after we distribute all the valence electrons. I think that is good. That is valid. How do I know it's valid? Because every atom attains the octet with 20 electrons there. Whether this is the most likely loose structure, we need the formal charge, right? So here, I would like to use this shortcut to help us to determine the formal charge. We see the single bonding oxygen. Single bonding oxygen has a formal charge of -1. All right. We got the 2 oxygen with -1. Remember, the overall charge is -1 as well. When we add up atoms with their charge, the overall charge must be -1. Now we got the 2 oxygen with -1 charge each. Together, that would be -2, making chlorine, you got it, +1. In case like this, we do not even have to bother to check out the formula of the formal charge if we know the shortcut of oxygen. Apparently, this is not the most likely loose structure. Remember, the more zero, the better. I do not see any zero in that loose structure, right? So that is why this definitely a not most likely loose structure. we need to find the zeros. In order for oxygen to have a zero formal charge, we realize oxygen has to be double bonded. That means, okay, so one of the lone pair on its oxygen will go to the bonding position to become double bonded. Now, question is, if two more electrons join into bonding, is that okay for chlorine to have 10 valence electrons? Yes or no? Yes. Why? Because chlorine is in the third period. Right? So if that's in the third period, we know for sure it is okay for chlorine to have an expanded octet. Alright, so now that chlorine can have an expanded octet, we established that we just put up a double bond between oxygen and chlorine. Just for one. Alright, so now let's see. This oxygen must have a formal charge of 0. This oxygen is -1. What's the formal charge of chlorine here? 0. And the resonance, right, of the other one will be as such as well. You might wonder, what happens if I have a 2 double bonded oxygen? Sure, let's do that. 2 double bonded oxygen now that we have 2 zeros on oxygen, but this time chlorine has -1. Would that be a good idea? For chlorine, the one with the less electron negativity, to have -1 charge. Remember, oxygen is the second most electronegative element. So we realize that is the one that we're going to have a problem with. So now we realize, okay, so we got the 2 most likely loose structures to represent. So we kick that out. Now let's do the shape using VSEPR. Remember, for the VSEPR, we need to count just how many electron groups we have on central atom, which is chlorine. Alright, just how many electron groups we have? These are the 2, okay, the most likely loose structures, so we better start with them. As we count, this is 1 electron group, regardless double bond, triple bond, type of bond. That is another one. So we got a 2 bonding pair, and we got 2 lone pair. This one is going to be the same as well. 2 lone pair and 2 bonding pairs. So from this 2 most likely or equally loose structures, we realize the 4 electron groups, and arrangement would be tetrahedral. The shape of the molecule should be bent. But before we leave that slide, one thing I'd like you guys to understand. If we try to count for this one we understand it's not the most likely loose structure, but it is still valid. If that is valid, let's count just how many electron groups we have in there. 2 bonding pairs. How many lone pair? 1, 2. Regardless of most likely loose structures or not, all we need for the VSEPR is 1 valid loose structure. Because for VSEPR, we really don't care which bond should be double, which bond should be triple. Okay, because triple, double, they both counted as one electron group, same as a single bond. It doesn't matter for VSEPR theory whether it is the most likely loose structure or not. All we need is one valid loose structure. All right. That is all for our final exam. We got 6 more slides where we're going to discuss a little bit more about the polarity of the molecules. That is for the students who's going to take Chem 2 class. All right, we actually touched a little bit of a bond polarity as we try to explain why electron activity can be used to unify the covalent bond and ionic bond together. Remember, for covalent bond, we have 2 situations. The first one, we got a bonding pair equally shared, like these 2 hydrogen, nice and easy. They're all smiling, they're both smiling. Why? Because they feel very comfortable to have those bonding pair equally shared with them. If we want to check out the electron activity between the bonding atoms, it is 0 for difference because they're the same atom. Right? So delta En is a 0. That actually can be used to determine the polarity of the bond. Because 0 as the electron activity difference for a bonding pair, we call such covalent bond a pure covalent bond. And the bonds between the 2 nonmetal atoms with the equal electron activity. And this is how we describe the pure covalent bond between the 2 atoms. And we see those electrons here staying right in the middle. And this is where we see the electrons stay right in the middle. And for pure covalent bond, there's no polarity whatsoever, no charge buildup. So that is the reason why we also call pure covalent bond as a nonpolar covalent bond. And we got quite many nonpolar covalent bond in the very thin substances, like diatomic elements. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. There are 7 diatomic free elements. And some people come up with Brinkerhoff to help us to understand, to memorize. Okay, so these 7 diatomic free elements. From this discussion, I just want you guys to realize if we find out 0 in difference of electron activity between the bonding atoms, such bond must be treated as non-polar. Pure covalent bond, no polarity whatsoever. It doesn't have to be the same atom. Remember, we have the table for elements with the values of electron activity. If we do have 2 elements with the same electron activity, such bond must be the pure covalent bond. For example, nitrogen and chlorine. Both have 3.0 as their electron activity. The bond between them, nonpolar. CS2. Both carbon and sulfur has 2.5 as their electron activity. Difference of electron activity, 0. Nonpolar bond. No polarity whatsoever between carbon and sulfur bond. So this is something that I want you guys to remember. And of course, we could have the bond where the bonding pair is no longer equally shared, like chlorine and hydrogen. Chlorine, hydrogen, 2 different elements, And we know for sure they have different values of electron-activity, meaning there's a non-zero value in the difference of electron-activity between the bonding atom. Since it's not zero, the bonding pair is no longer equally shared. As a result, there's going to be more electron density on element or on atom with the more electron activity, less electron density on the atom with the less electron activity. More means more negative charge, because we talk about electron density. Electrons negative charge species. So more electron density, meaning such atom must carry some kind of a negative charge. We do not know exactly value of the charge, so that's why we use delta. Delta to represent a charge somewhere between 0 and 1. Why can't we just get those values, figure it out? Because there's no need. This delta minus delta plus has already made the point for the polarity of such covalent bond. That is all we need. Since there's a charge buildup, the bond is polar. So we call the polar covalent bond. Speaking of notation, we can put delta plus on less electronegative atom. Delta minus on more electronegative atom. But it is the second that I like the most. We use arrow. Arrow starts with the less electronegative atom, point all the way to atom with a more electronegative. We use a plus sign to let people know, all right, this is where the element has less electronegative. All right, we are talking about the two different covalent bonds. One is pure covalent, nonpolar. The other one is what we call a polar covalent bond. And for pure covalent bond, we understand there's no charge buildup. For polar covalent bond, there's a charge buildup, only partial. Why partial? Because for ionic bond, we got a whole unit. Ionic bond is an extreme, as we discussed at the beginning of this chapter, extreme of a covalent bond, though that is the other side, the extreme on the other side. Another extreme would be the pure covalent bond. So the polar covalent bond is right in the middle of it. With the ionic bond, whole unit of charge, pure covalent bond, zero charge, somewhere in between, partial. So this is a very important statement I want you guys to realize, because okay, so maybe you could see some of the questions show up as maybe bonus or extra credit, okay, in our final exam. So telling you which bond is polar, which bond is non-polar. Just how are we going to determine the polarity of the bond? All right. For pure covalent bond, we understand that the negative electron activity difference must be 0. And bonding pairs equally shared. But if you take organic chemistry, people usually think a carbon-hydrogen bond as pure covalent. Okay. And for a lot of reasons, just try to simplify it. Okay. So that's just for your information. For pure covalent bond, there's no polarity in the bond, and there's no partial charge buildup. If we have a non-zero for the difference of electron activity, so we now see there's going to be a polar covalent bond, and the difference can be no greater than 2.0. 2.0 is the limit. The greater the delta En, the more polar the bond it is, the larger the partial charge, and the more ionic character this covalent compound is going to be. The greater the delta En, that means it's getting more closer to the limit of 2.0. Just what happens if we have a bond where the delta En is equal or greater than 2.0. We're talking about ionic bonding in this case. Okay. And for each atom, we talk about a charge. We talk about a cation and an anion because they carry the whole unit of charge. So this is how we can differentiate the polarity of the bond. The mass measurement in numbers for polarity is called the dipole moment. So that's a quantitative measure of the magnitude of the polarity of the bond. And of course, I just try to repeat this thing again. Delta En can be used to determine the polarity of the bond and how great the polarity of the bond it is. The greater delta En, the greater the partial charge, the greater the dipole moment of the bond, and the greater polarity of the bond, of course. And also, in order for us to realize just how great the difference of electron activity is, basically we can look at just how far apart are those two elements in our periodic table. If the two elements is right on top of each other because they're the same, it's a 0. The further away between the two elements, the greater the difference in electron activity between the two atoms. And it is my recommendation that we use arrow to show the polarity of the bond. Remember, arrow starts from the less electronegative element to the one with the more electron activity. And the greater the dipole moment, the greater the polarity of the bond, the longer the arrow. For pure covalent bond, there's no such arrow because there's no dipole moment, no charge buildup. We do not have element to start with because they have the same electron activity. Well, diatomic molecule, all right, it can be polar molecule if we got a polar bond within, and we got a nonpolar molecule if we have a polar bond within. Remember, diatomic molecule, there's only one bond. Polar or not determines the polarity of the molecule. What happens if we have a molecule that has 2 or more atoms? That is going to become a little bit more complicated because we're talking about the molecular dipole moment instead of dipole moment of the bond. The dipole moment of the molecule is a net dipole moment of the entire molecule. That means we have to consider the geometry or molecular shape of such compound. For example, C2Cl2. According to our nomenclature, we call it dicarbon dichloride. This is how the molecule is after we practice Lewis-Dot structure and the Vespers theory. Remember, we got a subscript of carbon, which is the central atom. That means we got 2 central atoms. And we find out it's a linear, right? Why it's a linear? Because for each carbon, 2 electron groups. 2 electron group is linear as its electron group arrangement or electron group geometry. And we find out this molecule actually is nonpolar. How do we know it? Because although we realize we got a polar bond between carbon and chlorine, but the 2 bonds, they are pointing to the opposite direction, meaning they cancel out each other. entire molecule does not have any dipole moment. And here, we actually call this compound dichloroacetylene. That is the nomenclature for organic chemistry. Because organic chemistry pick up any compound that has 2 or more carbon bonded in the compound. Even with the polar bond within, C2Cl2 is considered as a nonpolar molecule. Now let's look at water. Water, H2O, and this is the shape of this water, and we understand that it's going to be a bent. And definitely there's a polar bond within, because oxygen and hydrogen, we see the difference in electronegativity. Hydrogen is the least, right? Least electronegative nonmetal element. So when hydrogen bond with another nonmetal element, hydrogen always is going to be the one that have plus sign on the top to draw the arrow towards the other nonmetal element for the polarity of such bond. Once we realize for the bent shape like this, and 2 arrows, although they point somehow in a different direction, one going down, one going up, but they are not completely opposite. They're always going to be somewhere, something that's point out to the right. So if we combine these 2 arrows together, we realize they do not completely cancel out, and there is going to be the arrow inside the molecule, which is a polar molecule. Since there's an arrow, the polarity in the molecule, H2O is a polar molecule. That is very important. Water has to be the polar molecule, because if water is not a polar molecule, our recognition of the water is going to be totally different. Okay. Just how can we understand those arrows, whether those arrows can cancel themselves, like these 2 arrows cancel out themselves, and those 2 arrows not only partially cancel themselves. We can use the concept of a tug-of-war. Tug-of-war tells us if we got multiple pulls, and if we find out the center of this pull does not move, molecule is nonpolar. So if it's a stay put, molecule is nonpolar. If the center of molecule moves, molecule is polar. All right. As the summarize for everything, especially something involved the VSEPR, and we understand for the general procedure, we write about a Lewis structure. So here I give you the layout in the steps in writing Lewis structure. Remember, that is the fundamental. And we're going to need the VSEPR theory to determine the molecular shape. We count the number of electron groups. We determine the geometric arrangement for electron groups. So that's another name for electron group arrangement. And we determine molecular shape by taking account of this lone pair electrons. Once we determine the molecular shape, we can actually determine whether molecule is being polar or not. But before that, we need to determine the polarity of the bond. All you have to do is check out the difference in electronegativity of this bonding atom. If that's a 0, fine, nonpolar. If non-zero, for delta En, it's polar. As we just realized, even with the polar bond within the molecule can be nonpolar. That means not only do we have to count the polarity of the bond, we also need to count whether this molecular shape can cancel the polarity of the bond. The best way for us to do it is using the method that we call the tug-of-war. to see whether the center is going to move. If center moves, compound is polar. That is all for chapter 8 I'd like to discuss. And I thank you for your time. And it has been the greatest semester, the harsh one, no doubt. And I appreciate you guys for all the hard work that you guys have done. And good luck with the final exam. Thank you.